Okay, so we're going to continue this hands-on experience, and this is probably a nice segue into Kathy's presentation, because we'll take that 6 hours down to maybe 30 minutes using direct broadcast. So now I'd like to introduce Kathleen Strabala. Kathy's over 20 years working as a scientist at the Cooperative Institute of Meteorological Satellite Studies at the University of Wisconsin-Madison. Her primary responsibilities include cloud detection and cloud composition as determined from polar orbiters, and she's worked extensively on delivery and use of direct broadcast satellite products by global operational environmental forecasters, including the National Weather Service. So welcome, Kathy. Do you know where to go? I hope so. No, I don't. No, I don't. Yes, I do.
Thank you, Christy. I thought you were starting out by saying I'm over 20 years old, and that's certainly true. Okay, thank you. I'm going to talk about other data delivery methods, and specifically that will be direct broadcast and GEONET Cast. So we are led at the University of Wisconsin by Liam Gumley on this project, and that's the Cooperative Institute for Meteorological Satellite Studies. So if you're not familiar, direct broadcast is a real-time transmission of Earth observations from the spacecraft to the ground. So as the instruments are taking their obs, they're also transmitting data. So if you have an antenna, you can acquire the data with lowest latency for your local processing for local and regional applications. So SUMI MPP and NOAA 20 direct broadcast real-time via X-band with no encryption, licenses, or fees. So if you can acquire the data, NOAA provides software so you can create something useful from it. So this is the payload, which has been showed a couple times today. We're going to concentrate today on 3 of the instruments, the microwave sounder, ATMS, the hyperspectral sounder, CRIS, and the imager, which is VIIRS. So if you're unfamiliar with direct broadcast or antennas and ranges, on the lower left, excuse me, it shows a typical set of overpasses for one day for one antenna. Now, these antennas are located all over the world. At Wisconsin, we manage a number of them, but this is one that is centered on our location, which is in the middle of the North American continent in Wisconsin. And you can see there's a dashed line here, this circle, and as long as any of these orbits fall within that dashed line, we can acquire and process the data at our center. So, and the fact that these instruments take large swaths of information, for example, VIIRS has a 300-kilometer swath, you get good coverage. And this is just from one antenna from one satellite. So if you're looking for these orbit tracks, we have an archive for both SUMI MPP as well as NOAA 20. And then if you just want to take a look at 1 day's worth of passes that we got and acquired and created true color imaging from, that would be in the lower right example. So if you've never seen one of these antennas in operation, they're pretty impressive. Here's one that's located on the roof of a building in Honolulu, which is positioning itself, getting ready to start acquiring data on the horizon. So these are big, strong pieces of equipment. They move rather nimbly. You don't want to stand too close to them when they're operating. So the CSPP LEO, or Polar Orbiting Software, is a collection of freely available software for processing data from polar orbiter meteorological satellites. It supports the creation of observation data, so calibrated geolocated data, geophysical derived products, level 2 or EDRs, it's also called, as well as mapped images, and we're funded by the NOAA JPSS program office. And on the last portion of the slide, it shows where the software is distributed from, our website. So we not only support JPSS, SUMI MPP, and NOAA 20, but some of the software also supports other satellites, including MEDOP, NOAA 1819, Terra Aqua, as well as GCOM W1. The data source for the software input is usually direct broadcast, but it can also be NOAA class or the NASA DAC archive. And we've mentioned NOAA 20 a number of times today. NOAA 20 is being received for direct broadcast, and the software works on the data, and as it goes out its checkout period, the data looks great. So now there'll be 2 ATMS, CRIS, and VIIRS instruments. So this is the current suite of CSPP software. It consists of 14 different products, actually 13. We're just about to release the flood package. And I want to point out that there's includes these. I point out the enterprise algorithms that are included. So these are actually the NOAA satellite packages, the NOAA enterprise algorithm packages. I'd like to point out, take a couple to say a few more words about the SDR software. So that's the sensor data record software, the calibrated geolocation software for both SUMI MPP and NOAA 20. We also release a polar to grid package, which allows you to create high quality reprojected imagery, including true and false color, very easily. And then Hydra, which was mentioned a little earlier, is distributed freely through this site. And that's a tool that we use when we teach direct broadcast workshops. It allows interactive visualizations, cross comparisons between microwave, hyperspectral sounders, and imagers. It's a nice tool. So this is a matrix of the software and the instruments and satellites that it supports. So as you can see, one of the benefits of this and having enterprise algorithms is that it's the same science, so you get consistent retrievals with a number of different instruments. And the value of that is, for example, if you get the ClaverX software and you have data from all of these instruments, you can create consistent products from, let's say, so ClaverX or the cloud retrieval, it's the enterprise algorithm from NOAA. So now you can support VIRS on SUMI MPP and NOAA 20. You can support AVHRR on MEDOP A and B, NOAA 18 and 19, as well as MODIS on Terra and Aqua. So therefore, you can support 8 different instruments for one day, many orbits, which means latency is really good. The temporal refresh of those products is really good. So we have a number of ways that we distribute direct broadcast. One of them is through our real-time HTTP server, which is a rolling 7-day archive. This is the website for that. There's a number of directories underneath it, including level 1 products, level 2 products, and then there's an imagery as well. And if you're looking for a product dictionary for the full suite of products, if you go to the short course website, it's included in there. So I give an example of where you would find SUMI MPP, VIRS, SDR for one particular time period. So we also deliver and help our partners deliver a subset of products to the National Weather Service. So the data is acquired at these antenna sites, processed as quickly as possible, reformatted for AWIPS display and sent out. And we currently support all of the National Weather Service regions, including Guam now. So we also supply the data to SSCC Real Earth, which is a web mapping server that that's able to display a number of different environmental products. And then we also have a simplified web interface we call the Direct Broadcasting System web browser. So it's great that we can create all these products, and as we've seen today, the most important thing is that they're actually useful. So shortly after they started using direct broadcast in Alaska, it started having some benefit to them. So this was a article that was published in Space News in March of 2013, NPP satellite providing tangible benefits for weather forecasters. So we've got to our hands-on exercise now. So what I'd like to do is to look at a VIRS day-night band image from our real-time web server off the developing nor'easter or the bomb cyclone from January 4th to see the unique things that you can identify at night using the VIRS day-night band. So you can use the link on the workshop website to access the image. So I'm going to go there myself. So here's the website, and it's the last link under the 10:30 slot. If you click on that, it will show you this image. So this was acquired at our center, processed in near real time, and posted to our website as soon as possible, along, of course, with the actual data files themselves. So if you're unfamiliar with the VIRS day-night band, so it's a band that can sense visible light even at night. It's sense enough to be able to detect the visible light that reflects from the sun off the moon to the Earth atmosphere system and back out the top to the sensor, or anything that emits visible light at night. So as you might imagine, what these images look like is highly dependent upon the phase of the moon. In this case, from January 4th, it was almost a full moon. So the first thing you'll notice about this image is that it looks very much, the clouds look very much like a visible image. So low clouds, high clouds, thick clouds are very bright. Thin clouds, like cirrus, don't reflect nearly as well. You can see things like snow. So this is This is South Carolina, Georgia here. You can see that, and so I wanted to ask the questions. Why is it important to be able to see things like snow at night? I can answer that question if no. Yes, Eric.
Well, that will change your radiation.
Very good.
balance in the boundary layer and temperature.
Right. So if you're a forecaster and you want to know where that boundary is, what are the low temperatures going to be like for that night, for example? Okay, some of the unique things that you can see. You can see the city of Atlanta comes through very quickly, very clearly, and other cities as well as roads that you can see. Now that's something that you wouldn't be able to see in infrared. So why would that be valuable to be able to identify those features? As we heard earlier today, if you look at this image and then perhaps there's a big storm that went through, you might notice that there's not as many lights on, for example. So power companies are very interested in this. If road lights are out, it's very important for transportation purposes to know that. So that's one other application. And also, I wanted to show, sorry, I'm not a Windows user. So it's very, very easy on this image to see the low clouds. And oftentimes with tropical cyclones, other cyclones too, the low center circulation at the surface is obscured by high clouds. And in the IR, the high clouds or thin cirrus can really dominate that scene because they're cold and high. But in the visible, you can see oftentimes right through them. So that makes it very easy to locate to identify the center of the storm. And because you can see low clouds, things like fog at night are very easy to detect. They're small water particles that reflect during the daylight very strongly, but at night they're often nearly the same temperature as the surface, so they can be very difficult to identify. Okay, so I just wanted to show you that this is one image from one pass that we acquired. We get these all the time, and we process them as quickly as possible, and in direct broadcast, they can be out there in near real time. Okay, sorry. Getting back to our presentation. So I wanted to just say a couple words about low Earth orbit versus geostationary environmental satellites and some of the advantages of LEO versus GEO. First of all, the LEO provides global coverage. It's orbiting the globe from pole to pole. It typically has higher spatial resolution. VIRS has 22 bands, including the VIRS nice band, and this becomes more and more prominent as you go to higher latitudes. It has more spectral bands, including unique bands like the day-night band. The VIRS instrument actually contains the actual red, green, and blue wavelength observations. The geostationary, like GOES 16, actually doesn't contain a green band. Now that we have multiple satellites, it'll never replace the temporal coverage of GOES and the value of that. But we have much better temporal coverage now that we have enterprise algorithms available that can have consistent science retrievals from multiple satellites. And the fact that we can do this in near real time with the direct broadcast makes it very valuable. We also have instruments including a microwave and hyperspectral sounder, which, as we've seen, are critically important for numerical weather prediction. And what we like to say is that the LEO and GEO platforms and their advantages and disadvantages complement each other. So I just want to say a couple words here at the end about GEONET Cast, which is another way of distributing data. So its mission is to provide environmental data through communication satellites from regional partners. So it, again, for sound decision-making for local government agencies, for example. So the idea is that these regional systems will disseminate data based upon digital video broadcast technology. So it's a low-cost way of distributing and acquiring products that are useful to the environmental decision-making community. Now, currently, I heard that there's actually one VIRS product that's distributed via GEONET Cast now, and that's, I think it's the VIRS NDVI product, but NOAA plans to distribute many more products through this method in the future. So this is a global coverage of GEONET Cast right now. So the partners are NOAA, and that's for North and South of America. Then there's EUMETSAT, and then CMA also distributes data via this method. So again, the whole idea is to disseminate high-volume data worldwide, even to areas with limited access to the internet. So if you want to find out more information, including the current suite of products, you can go to this website. So in conclusion, the JPSS project continues to support new and better ways of distributing products to end users. Direct broadcast provides the lowest latency in the creation and delivery of these products, and the goal of CSPP LEO is to facilitate the use of environmental satellite data for local applications, and NOAA is working on distributing data via GEONET Cast as an effective, inexpensive way of providing useful JPSS products to regional users. Thank you.
Thank you. Thank you, Kathy.